So, hello everyone, my name is Sebastian, thank you for joining. I'm gonna give this talk jointly with Sadra, and it's based on our work that is currently in progress and we hope to finish soon. So what we're gonna discuss is how to compute loops and inflation and what are the potential observables that we can extract from them. It's based also on related work done by Sadra and collaborators. So I'm gonna start by giving you some contents. So first we're gonna discuss what is called the cosmological collider signal. Then we're gonna talk about a particular example, which is called the phonon collider. Then we're gonna write an EFT for these phonons, and we're gonna end by extracting observations from these EFTs. So now we're gonna discuss the cosmological collider. So when we look at the sky, the way that we make observations is by taking correlation functions between different points. So for example, here we have a correlation function between 3 points forming a triangle, and here we have between 4 forming a quadrilateral. So these correlation functions encode a lot of information about the different epochs of the universe. For example, the galaxy formation, the dark matter abundance, but also, very interestingly, they potentially can have information about the early universe physics, in the sense that if inflation happened, this could potentially lead to an imprint over these correlation functions. One of them, so before starting the discussion, I'm gonna set some of the notation. We're gonna look at FRW metrics, which are close to being the zeta. By that I mean that the scale factor is given by 1 over h eta, where eta is a conformal time that runs from minus infinity in the past towards 0 in the future. This will imply that the scale factor was very small in the past and keeps growing towards the future. We're going to be interested in computing correlation functions of field that evolve from the past, where they were in their vacuum, towards the future, where we're going to make the observation. That means that we make the field evolve from some point here, and then on a fixed time, very close to the asymptotic future here, we're going to take some time slice where we're going to compute the correlation, the field profile. So one of the most important examples when looking at correlation functions in the sky is called the cosmological collider. So now let's imagine that we want to compute the correlation functions between 4 different points. So we take the field on a fixed time slice and we compute the value of the field on 4 of these different points. Now, it could be the case that before this field reach the point where we're going to make the observations, they exchange a particle of mass m. Now, very interestingly, there will be properties of this mass m encoded into the 4-point function. So because if in the most simple example, we assume that we were on the zeta spacetime, most of the information is encoded by the symmetric properties of the spacetime, but also because there are many analytical properties of this correlation function. So for example, this 4-point function can be decomposed into 2 pieces, one which will be analytical in the external momentum and also on the exchange momentum that I'm calling S, but also there will be an analytical part that will depend on non-perturbatively on the mass of the field exchange. So this has important consequences because then we potentially can obtain crucial information about this mass encoded in the past. Now, how do looking at the chain function? So for example, in this case, to make our lives easier, we're gonna consider only a 3-point function where a particle of mass m was exchanged in the past. So the shape function is obtained by multiplying the correlation functions times k1, k2, and k3. So if we look at this, we see that depending on the triangle formed by this 3-point function, there is different information. So when the triangle becomes more equilateral, it will be suppressed by the mass of the particle. But very interestingly, for the squeeze limit, so which is when one of the sides of the triangle is much larger than the other two, the signal will be proportional to exponential of minus pi m over h. And also, it will be some oscillatory signal. This is unique of the fact that there was a particle interacting in the past, and in the case that there were no particle, the signal will be very suppressed. So by detecting these kind of shapes, we will have a unique signature of the particle happening in the past, getting access to physics at very early in the universe at very high energies. Now, there's been a lot of progress in the recent years in understanding correlation functions, but most of the work has been focused on correlation functions at tree level. This is because computing these things are particularly hard. The problem is that there are many cases where all these effects start appearing as loops. For example, we want to couple the scalar fields from inflation to standard model particles such as fermions or even the Higgs. All the couplings will appear in this form. For example, in this case, which I have a phi dot and two fermions. That will imply that when I want to look at the 3-point function, the first coupling will appear at a loop level. So where in this case, I have these three external legs of phi, and there will be fermions running into the loop. That implies that in order to understand this, we have to get a lot of knowledge on how to compute these loops. This will also have interesting observational consequences. For example, it could lead to new shapes of non-Gaussianity that are not related to the ones that have been discovered before. But also, one of the problems of the cosmological collider is that the signals are very suppressed, and it will be possible to enhance them by having many particles running inside these loops.
Hello everyone, my name is Sadra Jazayeri, and I'm going to continue with Cosmological Phonon Collider. So the phonon collider is basically the same as the Ceter collider, except that we want to relax the Ceter isometries. So according to this old famous paper, Effective Field Theory for Inflation, one can think of inflation as a state of matter in which the time translation symmetry is spontaneously broken. So basically, we have an almost shift symmetric sector and with an internal shift symmetry, which acquires a time-dependent wave, almost linear in time. And this time-dependent wave breaks the isometries of Poincaré down to a subgroup, which is basically a diagonal combination of the time translation symmetry and shift symmetry, and also, of course, the Euclidean group, which describes the isotropy and homogeneity of our universe. So the idea is that one can describe the scalar fluctuations during inflation in terms of the Goldstone boson that nonlinearly realizes this time translation symmetry. So when we have gravity, the transformation of the Goldstone under the time diffeomorphism is given by this formula. And if you ask this diffeomorphism to hold, in addition to asking the quasi-de Sitter background to be a solution to the theory, almost fixes the entire form of the Goldstone boson pi. So the most interesting aspect at the quadratic level is having a speed of sound. So breaking the boost led you to have some reduced speed of sound. And because of the symmetries, again, if you have a reduced speed of sound, immediately you should have some amount of interaction, a cubic operator, pi dot nabla pi squared, with this coefficient. If the speed of sound is very small, then you have big non-Gaussianity, which will be otherwise ruled out by Planck. Therefore, due to the bounds, the observational bounds, we have some lower bound on the speed of sound. So all in all, what this tells you is that you have an effective field theory for the pion, for the phonons. Also, we can call it phonon because the symmetry breaking pattern that I showed is the same as the superfluid at zero temperature. So the longitudinal sound waves obey the same sort of effective field theory. So I'm going to call this phonon from now on. So all in all, what this tells you is that you have an effective field theory that has a regime of validity. So it has a strong coupling scale given by this value, where f pi is the symmetry breaking scale fixed by the observational value of the scalar fluctuations. So due to this bound, f of pi is almost 58 Hubble, and then the strong coupling scale is this. And in this regime, between lambda and Hubble, you can use this effective field theory to make predictions. So now the natural question is that what happens if I couple additional matter fields to the effective field theory for inflation? So we're going to focus on relativistic species, which have a relativistic dispersion relation in the flat space limit. So for example, I could consider scalar fields or, for example, fermions. And now you can ask, so this relativistic species will obey Lorentz invariance at the quadratic level. That's my assumption. And then once I couple them to the effective field theory for inflation, of course, the boost will be broken. So now, in order to write down a consistent effective field theory that describes the interactions between these relativistic sectors and the phonon, the most straightforward way to do that is to go to the unitary gauge, where you use the time diffs to kill pi's, to set pi's equal to 0, and of course the scalar degrees of freedom do not disappear; they will be eaten by the metric. And then in this gauge, you are allowed to write operators that are invariant under spatial diffs only. And then you have a list of possibilities. So you can write, for example, delta G00, which usually you don't write in the covariant theory, but here you're only constrained by spatial diffs, so you can. And also, in addition to that, you can add covariant operators. Sorry, not this one. Covariant operators, and also the zero component of vectors. So the effective field theory derivation is straightforward, and then once you have the effective field theory in the unitary gauge, you can do the Stuggelberg trick by performing a diffeomorphism that is dependent on your phonon, and then you get a bunch of operators that mix pi with the heavy fields. So all in all, you will get a series of operators, for example, pi dot squared, sigma squared, pi dot sigma squared, or similar terms with the fermions and so on. And these will naturally appear in exchange processes that contribute to the correlation functions of pi's. So unfortunately, computing these graphs, especially when you have heavy fields in the in formalism, is very complicated because we don't have time translation symmetry in the CTER, and the mode functions for heavy fields are complicated. They're Hankel functions. So we have very few analytical results, except for the recent progress, the recent explosion in the bootstrap literature, where we use similar tools as conformal field theory to bootstrap the graphs. And these are primarily limited to 3 level, although there are a few results also about loops. So let me just summarize what is the strategy for computing this if we were to just do the time integral. So basically, in the so-called Schwinger-Keldysh formalism, the graphs, the perturbative graphs, are organized in terms of a series of vertices which come in 2 types, plus and minus, corresponding to the Schwinger-Keldysh plus and minus contours. And then for each, when you want to connect the vertex to the boundary, you have to insert some bulk to boundary operator. So, I mean, what is important here is that, for example, for the pion, these are given by the positive and negative frequencies of the positive and negative frequency mode functions, and for the phonon, sorry, I guess I said pions. For the phonons, what is important is that when the mode exceeds the sound horizon, pi freezes. So this is the difference with respect to the slow roll, where the freezing happened at the Hubble scale. So here it happens earlier at the sound horizon crossing. And if you want to also connect vertices in the bulk, you have to insert bulk-to-bulk propagators, which come in 4 different ways. And at the end, you have to compute some time integral. So associated with each vertex, you have an integral over the conformal time eta. And because of these time integrals, the computation analytically is usually very cumbersome. However, in a limit where the speed of sound is small, a natural hierarchy of scales emerge, which simplify this computation, which I'm going now to describe. So the hierarchy is the following. So you have 3 length scales which can fall into this hierarchy. So basically, on the right, you have the horizon that sets the curvature of the CTER. Then you have the Compton wavelengths of the heavy field, which I assume is bigger than, the length scale is smaller than Hubble, so the mass is heavier than Hubble. And then you have the sound horizon. So what this allows you is that, so it shows that we are in this situation where the redshift of the expansion makes the modes to first exit the sound horizon before they hit the mass shell. So what this describes you, what this allows you to do is to first observe that the time derivatives of the phonons at the sound horizon crossing, they are of order Hubble, whereas the special derivatives are of order Hubble over the speed of sound, which is, when the speed of sound is very small, it's much bigger than the time derivatives. So this is important because you can imagine, because the mass is much bigger than Hubble, you might think that, oh, okay, so I can just integrate out this massive field. And you can, but the important difference with respect to CS equal 1 is that the effective field theory that you end up with after integrating out the heavy field, it is organized as some sort of derivative expansion. So the time derivatives are suppressed by 1 over m, special derivatives also by 1 over m. However, the time derivatives are much smaller than the special derivatives. Therefore, you might be in a situation where you can expand in time derivatives, namely, you have an effective action that is local in time. However, the special derivatives are not small compared to mass. And that is exactly the hierarchy that I was talking about. And then you have to keep the special derivatives non-perturbatively. So you end up having a especially non-local effective field theory in a space. So this is basically the idea. So we are going to assume that we are in this hierarchy, and then we compute some effective action that Sebastian is going to next talk more about. But let me just say that at the 3 level, what does this approximation amount to? So the approximation we are in, it tells us that for the bulk-to-bulk propagator, for the Feynman propagator, basically in the equation of motion, we can ignore the time derivatives, and the bulk-to-bulk propagator is basically proportional to a delta function. So it means that the force that the heavy field is exchanging between pi's is instantaneous at leading order. Of course, the retardation effects can be captured by expanding in the time derivatives, but at leading order, this means that you have an exchange diagram, you start from an exchange diagram, you integrate out the field, and you end up with some non-local effective action, which I let Sebastian to further on. Thank you.
The other one doesn't matter. Now, a bit into more details, when we integrate out this field sigma for the interaction that I showed you before, I can write down the correction of the action from the Wilsonian action as something like this. I will have 2 fields here, 2 fields here, and then there will be the square of the propagator like this one here. So this is actually very much as the loop and how it will be interacting as a vertex. Very interestingly, this thing, when the mass goes to infinity, should only be reduced to 0, and so this effect will be only, so it would can be understood as a vertex effect. So if we take a look at this propagator, it can be written as 1 over the box square, which is given in the zeta spacetime, minus m squared. Now, because we're considering phonons, we can take a further simplification by taking a look at this. So if we expand this box operator, then we know that this will go as CS squared times the eta squared minus nabla squared over a squared. But because CS goes to 0, then we're going to consider a hierarchy where this term is suppressed with respect to this one. This will lead to a non-local EFT, where we can add a bunch of other terms that will have this particular form. But more importantly, this Feynman propagator is actually the same in Minkowski, where this term doesn't appear, and we only have to consider this one. So now let's compute an EFT for these phonons. When we integrate out a field sigma, what we do is the following. We take an action that will depend on the Goldstone mode pi and sigma, and we integrate over all the values of sigma by doing a path integral. This will lead to an effective action that will depend only on pi. But in general, the effect of the integrating out this sigma will be that this effective action is non-local. Usually, what you do is to assume that the expand on some parameter, for example, the mass of the field sigma, and make this effective action to be local again. In this case, we're not going to be interested necessarily in that, because there is a new regime that we can understand. So for example, if we take a look at the quartic vertex obtaining this effective action, it will be given by this. Schematically, it will contain the 4-point function, so pi dot to f4, and also it will be multiplied by delta f to f4. So all the non-localities are encoded in this term. We can see it from here because it will go as 1 over the box operator minus the mass of the field. Now, there is a further important simplification. Given that we're studying a theory of phonons, there will be a hierarchy between this time direction and the gradient, and we're gonna safely assume that this one goes to 0. This will become very important for us because this effective field theory, even though it's non-local, it actually is the same one in Minkowski where we only have these terms. Now, if we actually, what we can do is to do the loop integral. So for example, in the past example, this loop can be computed explicitly in terms of Feynman parameters. So now we see that the non-local vertex that is given by this term in red contain different pieces. It's proportional to the mass of the field, to the normalization scale mu, but also it will depend on the gradient like here. The main difference from the Minkowski case is just given that it now depends on the conformal time. So the thing that what will happen is that when we do the integral, when we compute the correlation function, we still need to do an integral over time for this. But very interestingly, this term is actually similar to a one-loop effective action for flat space. And this is very useful because that implies that we can use all the techniques from flat space and import them into this more complicated de Sitter problem. So for example, one of the things that we can do is to use spectral decompositions. So this comes, and this is useful because loops computations in de Sitter are very challenging, mainly because we don't need to necessarily consider. Okay, so let's take a look at the spectral decomposition in Minkowski. It has an important property that there is no particle creation for m prime smaller than 2m. That implies that this is actually 0, and it makes sense because of the loss of spatial relativity. Then for large m, this function will grow monotonically, as the one shown here, tending to a constant value. We can see quite explicitly that this function is always positive, doesn't contain any singularity, and has this region where it's 0. So that implies that actually the computation will be much easier if we're able to compute a loop using this technique. Now, very interestingly, the case of de Sitter is a bit different. So first, there is no particle threshold, but on exchange, what we have is that the spectral density is exponentially suppressed for very light particles. So that means that all this region, which is actually different from 0, will only contain a support that is very small. Now for nu prime over 2 nu, the spectral decomposition in de Sitter tends to the Minkowski one, but there will be an error which goes at 1 over nu prime. In the end, this tells us that the approximation we were using by considering the loops as if they were the particles in the loops as if they were in Minkowski, just give us a small correction that will go as 1 over nu prime that we can neglect on the first approximation.
The non-local effective action that Sebastian described can be used to compute cosmological correlators. So essentially, the interactions due to the heavy field, so the exchange and the circulation of the massive field, basically happens in the flat space limit, where I can think of this blob as some interactions that are happening in flat space. So essentially, we can work with some in-out Feynman graph that are contributing to the 2-point function. And they depend on, for example, a 4 momentum squared due to Lorentz invariance. And once I have this, I can compute the contribution of this graph to the effective action, the non-local effective action for pi. So this non-local effective action takes this general form. So once you have computed this capital pi in flat space, you can just deform the argument. You add the expansion of the universe as s squared eta squared. And then the rest of the effective action comes from what vertices you put in the original graph. So you will have some local derivatives of the pi, so on and so forth, depending on what is the structure of the original graph. So in order to compute the time integrals, it's actually much easier to introduce some seed integrals, some simpler forms of the time integral, where you are basically deforming the mode function into some simpler mode function of the external legs. So instead of working with massless field, you work with fields with ms squared equal to 2h squared, but with with the same speed of sound. So once you introduce this fictitious scalar field, the 4-point function transforms into a simpler form that is easier to compute. And once you have computed these seed integrals, you can derive a network of various graphs of pi by applying specific weight shifting operators that depend on the only on the external kinematics, as it was explained in these two papers. So at 3 level and at 1 loop, the Feynman graphs that contribute to the 2-point function are so for the bosonic 1 loop and for the 3 level, they are given by these expressions. So inserting this inside the time integral and taking a time integral is what we have to do, but there is an intermediate steps that will simplify our life, which is to instead work with the Mellin transformation of the propagators of these 2-point functions. So basically what we do is that we replace the propagator with some power law, with a complex integral over some power law in momentum, and we plug this we plug the capital pi, the Mellin transform of the capital pi inside the time integral and take the time integral. The time integral becomes very simple, so it's a gamma function times the power law. But then this simplicity comes at the expense of introducing a complex integral that we have to yet evaluate. So if you look at the Mellin transformation in the Mellin's complex plane, we see that usually, at least for these two examples, the 3 level and 1 loop, the integrand is essentially analytic everywhere except for some isolated poles at integer values of the Mellin variable. And you can make a suitable deformation of your original complex contour such that you pick up some residues, and then you can evaluate your f. So in our case, if we assume that we are in this regime where the intermediate momentum is bigger than alpha, which is Cs times mass, S is bigger than alpha times the total energy, then we should close the contour on the right-hand side at when the real value of z goes to infinity. And once we have done that, we find that at 3 level and at 1 loop, the 4-point function takes this structure. So you have some power law in the ratio between k total and the intermediate momentum multiplied by a logarithm. For example, in the 3 level, you also have a log squared in the case of a bubble. So this is the general structure that we find. What is remarkable about this result is that in hindsight you discover that although you assume that you have to assume that S is bigger than alpha kt, but if you check, you can see that the radius of convergence of this series is actually infinite. So you can just analytically continue these results everywhere. For example, at 3 level, this was discussed at length in these two papers. You find that if from this seed integral you apply a weight shifting operator and you go and compute the bispectrum is characterized by a bump in the squeezed regime where the squeezing parameter is of order alpha. You will see a bump which we called it lowest with collider signal. And that is a smoking gun imprint of having a supersonic exchange in the Feynman diagrams of pi. However, at 1 loop we don't see the same bump, so the shape remains to be still very similar to equilateral orthogonal, although there might be some other complicated diagrams that feature the same bump. This is still in progress. To summarize, we hope that during this talk, we were able to carry across this message that the cosmological correlators of phonons, when the phonons move at a slow speed, feature a lot of simplicity. In particular, we discovered an interesting interplay between cosmological correlators and flat space Feynman graphs in the slow speed limit. About the future, as I already alluded to, it would be interesting to see if in some other loop diagrams, the low speed collider bump will also appear, and whether the amplitude of this bump can be enhanced by some color factors. Other phenomenological applications in which our non-local effective field theories can be used includes the searching for parity violating signal in the trispectrum, for example. And we already had some work about the application of non-local FFT at 3 level, but it would be also interesting to see that at loop level, something similar can materialize. And finally, thank you all for paying attention to our talk.